In 10.1, we're going to discuss something called Taylor polynomials. And Taylor polynomials are a simple way to approximate a function near some value. So a Taylor polynomial of degree n approximating f of x near x equals 0. And that sounds a little bit odd. What do we mean by approximating it? But this will make more sense in a second when we look at what's happening here graphically. But to get the Taylor polynomial of some function f of x, you follow this pattern. You do f of 0, then you find f prime of 0. Then when you do the second derivative at 0, you put it over 2 factorial times x squared plus f triple prime of 0 over 3 factorial over x cubed and so on. So essentially, the idea is to find a Taylor polynomial you are finding the coefficients. And once we do a few of these, that'll make more sense. So let's go ahead and we're going to jump into it and start by finding our first in a very simple Taylor polynomial. So let's say we wanted to find the Taylor polynomial of degree 2 centered at x equals 0 for f of x equals cosine of x. So we want to find f of x equals p sub 2 of x. And really, I should put that's approximately. It's not the exact thing. It's approximately p2 of x, which is going to equal f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. So what I really need to find is these coefficients that are going to go on x and x squared. So let's start first by finding f of 0. Cosine of 0 is 1. F prime of 0. Well, we know the derivative of cosine is going to be negative sine of 0, and sine of 0 is 0. And then the second derivative, f double prime of 0. The second derivative would be the derivative of the first derivative, and the derivative of sine is cosine, so negative cosine of 0 is going to be negative 1. So let's plug those in up here. F of 0 is 1 plus f prime of 0 times x, so 0x, plus f double prime of 0 is negative 1 over 2 factorial, and 2 factorial is 2 times 1, x squared. So what we're saying is f of x is approximately p2 of x, which equals 1 minus 1/2 x squared. So what we're saying is near x equals 0, this thing, 1 minus x squared, is about the same thing as cosine of x. So what I've done is I've gone to Desmos and I've graphed these two things. So let's look at the graphs. The red is the graph of cosine of x. In the blue is the graph of 1 minus 1/2 x squared. And if you notice, in this area here, they're actually almost on top of each other, meaning 1 minus 1/2 x squared is pretty darn close to being cosine of x in that area. Let's take this a step further. We're going to do the Taylor polynomial for degree 8 of cosine of x. We already know we've done f of 0 was 1. F prime of 0 was 0. F double prime of 0 was negative 1. And if you remember the second derivative, right, the second derivative was negative cosine x. The third derivative, if you kept going, would be the derivative of negative cosine of x would be back to sine of x. And sine of 0 is 0. Continuing on, the fourth derivative. The derivative of sine is cosine. So we're back to cosine of 0, which equals 1. The fifth derivative, the derivative of cosine is negative sine of 0 is 0. The sixth derivative, the derivative of sine's cosine, so we have negative cosine 0 is negative 1. The seventh derivative, well, the derivative of negative cosine, back to sine. So we get 0. And then the eighth derivative, the derivative of sine, back to cosine, is 1. So putting this together, the Taylor polynomial of degree 8 is going to equal 1 minus x squared over 2 factorial plus, we would skip the third one and we would have to jump to the fourth one because we had a 0 for the third one. X to the fourth over 4 factorial. Jumping down here to the sixth one, minus x to the 6 over 6 factorial. And then jumping down here to the last one, 1 over 8 factorial. And if we multiplied all those out, we'll get 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720 plus, I should add over here, this would be x to the eighth plus x to the eighth over 40,320. That would be the Taylor polynomial of degree 8 for cosine of x. So let's look at what happens as we add terms. Now we have the graph of cosine of x in the Taylor polynomial of degree 8. If you look at this region, what's happening is the graph is fitting even better. It's stretching out. And our polynomial is even better matching cosine of x over a longer period of time. So as we add terms, we actually begin to model the function. Now, can you imagine if we actually continue to add terms, and if you think about what we've been doing, what does this thing look like? That looks like a series, except for we're cutting it off. So what we want to do is continue to add more and more terms, and if you had an infinite number of terms, you'd be getting pretty darn good, pretty darn close to the actual function. Now, the functions we've done so far were centered at x equals 0. And so we just had x, x squared, x cubed, and so on. But if you want to do one centered at x equals a, instead of having x, x squared, x cubed, and so on, you'll have x minus a, then x minus a squared, x minus a to whatever value of n you want to find. So there's just one little subtle difference. You're still plugging in the a value into the derivative, though, to get the coefficients. So let's do an example of this, but we're going to do near x equals 1. So let's just get the general layout. The fourth polynomial centered at x equals 1 is going to take on the form f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus the third derivative at 1 over 3 factorial x minus 1 cubed plus the fourth derivative of 1 times 4 factorial x minus 1 to the fourth. So really what we need to go through then is find each one of these coefficients so we can fill this in. Okay, so let's write out what these actually are, and then we'll go back and plug them in just so we can get the derivatives first. F of x is natural log of x. If we took the first derivative, the natural log of x, the derivative of the natural log of x is 1 over x. The second derivative, if we rewrote that as x to the negative 1, drop that down, reduce it, the second derivative is negative 1 over x squared. Continuing on, the third derivative would be dropping that down, 2 over, and it would become positive, x cubed. The fourth derivative, if we move that to the numerator, drop it down, you get negative 6 over x to the fourth. So I found the first four derivatives, and now let's just plug in 1. The natural log of 1 is actually 0. Plug in 1, 1 over 1 is 1. Plugging in 1 into the second derivative would give negative 1. Plugging in 1 to the third derivative would give 2. And plugging in 1 to the fourth derivative would give negative 6. Alright, so let's write our polynomial out. We would get f of 1 is 0 plus f prime of 1 is 1 times x minus 1. The next term is actually a negative 1. So negative 1 over 2 factorial x minus 1 squared. The next term is 2 plus 2 over 3 factorial x minus 1 cubed. The fourth term is actually a negative 6, so let's take that out. Negative 6 over 4 factorial x minus 1 to the fourth. And so if we simplified each one of those terms, 0, we don't need that. 1 times x minus 1, so we get x minus 1 minus 1/2 x minus 1 squared plus 2 over 3 factorial. 3 factorial is 6, so really that's just 1/3 x minus 1 cubed, and then we've got our negative 6 over 4 factorial. 4 factorial is 24, so 6 over 24, that's 1/4 x minus 1 to the fourth. And so that's how we do a Taylor polynomial that's centered at something other than 0.